Today we will talk about chemical reactivity and mechanisms, how we can account for chemical mechanisms in terms of thermodynamics and thermochemistry. We will start from basic concepts like what is energy, what type of energies are there, and how they are related to each other. Basically, this whole session is about exploring the relationship between chemistry and energy. And then we will talk about enthalpy, entropy, and Gibbs free energy. These are definitive thermochemical properties for a certain reaction, not just reaction, but any process. So we will talk about them step by step. So let's start with basic concepts. Here we will define what is energy, what's the law about conservation of energy, how we define temperature and heat, what's the difference between them, and we will learn something called state function. What is state function and what properties we have learned so far are state function and which are not state function. So we will talk about energy and nature of energy. So basically the definition of energy is a system's capacity to do work or produce heat. Specifically, when we talk about thermodynamics or thermochemistry, we'll focus on heat transfer that accompanies chemical processes, but at the same time we will talk about work. There's very important law about energy and how basically energy dynamics works, and that's called conservation of energy. And that basically says that energy cannot be lost for a reason that we cannot account for. That's the definition of law of conservation of energy. It states that energy can only be converted from one form to another, but it can never be created or destroyed out of nowhere. The energy of universe is constant, and when we divide universe into system and surroundings, system's energy can increase or decrease during the process, and surroundings same. I mean, when the energy of the system increases, surrounding decreases, and vice versa. But the total energy of the universe, which is the sum of system and surrounding, it's gonna be constant. There's always gonna be a reason for certain energy decrease or increase, which is accounted by this law of conservation of energy. And energy can be a potential energy, which we define as energy that's due to composition or position. For example, attractive and repulsive forces. They are actually type of potential energy. Or another example would be energy released when gasoline is burned. That results from the differences in attractive forces between the nuclei and electrons in the reactants and products. So it's basically we have some reactants and then they are burned and converted to products. So there is some energy difference. They will be in different levels. We will actually talk about this when we describe reactions in terms of their thermodynamic profile. We have certain level for reactants, energy level for reactants, and then energy level for products. So it means that energy goes down. Energy for the products is lower than the energy for reactants. So that difference is lost as a potential energy. So that's why we say energy is released when gasoline is burned. And there's also a kinetic energy. Kinetic energy of an object is energy that's due to motion of an object. And it depends on the mass, as you can see from this equation. It depends on the mass and velocity. And here we have an equation for potential energy, which is mgh. M is the mass, g is gravitational acceleration, and h here denotes height. So when we say energy due to position, we actually refer to energy due to height. The objects that are higher, they will have more potential energy. All right. So now I will try to explain law of conservation of energy using a simple diagram. So we have two balls, two objects here, A and B, and as you can see, A is held in this place with some forces. That's not relevant in this case. And as you can see from this initial state, there is a difference in position, difference in height. The object A is higher than object B, and this height difference, this difference in position, leads to potential energy of A being higher than potential energy of B. And you might recall a formula that relates potential energy to height, mgh, and height of A is higher, so that means potential energy of A is higher. initially, and let's say this ball is released. Ball A is released, and it's gonna come down and collide with B, and that will push B upper. And this is what the final state for this simple system looks like. So what happened here is we had potential energy for A. Because it's on the higher position, it has some potential energy. And when we release ball A, it's going down, it's losing its potential energy. But because energy is conserved, this energy should go somewhere. And as you can also see, A is moving. So that means potential energy of A is converted to kinetic energy of A, as a result of which we are having some motion. Kinetic energy is always associated with the motion of an object, all right? And so basically potential energy of A is converted to kinetic energy of A. And now it makes sense to define work here, which is a force acting on over a distance. So we have some distance and some force is acted on here. So here, as you can see, ball B will actually gain potential energy. This kinetic energy of A will be converted to potential energy of B. And that's the reason why we are having this B going upward. It cannot just go upward by itself, right? It means it should gain some energy in the form of potential energy so that its height can increase from 0. We can accept this as a 0 line and to some height h, right? So what happened here is that there's actually work that's done by ball A on B, okay? Object A did some work on B. So the energy transfer here occurred as a work. In the previous slide, we also see that energy, what's the definition of energy? It's system's capacity to produce heat or work. Here, in this specific instance, when the potential of energy A converted to potential energy of B, there was an energy transfer, right? And this energy transfer is done mainly due to work that is done by object A on B, okay? So energy is transferred through work here, mainly. I'm telling mainly because there's also another type of energy here that's not immediately visible from the system. So here we are saying that the work is required in order to raise B from its original position to its final position, okay? So the part of the original energy stored as potential energy in A has been transferred through work to B, and thus increasing B's potential energy. But there is this difference in heights for B. So B's final position, if you see here, is actually lower than A's initial position. It's due to friction. Because if the situation is like this, all of the potential energy of A is converted to B's potential energy, then we would expect B on the same level as A. But that's not the case. And the reason for this is as object A rolls down the hill, some of its kinetic energy during its motion is actually transferred to the surface of the hill as heat. Okay, so in that sense, energy is not lost. We can account for the whole transformation of energy. There is no any amount of energy that is lost and we don't know the reason why. We always know that, okay, energy is transferred through work and also heat, and there's no energy destroy or creation of new energy. And also the temperature of the hill increases very slightly as the ball rolls down. That increase is extremely negligible, but the friction happens and then temperature increase due to friction also is observed.